Now let's present transmission line measurements. The notion of simultaneity between cause and effect, as implied by ordinary electric circuit theory, closing a switch at some point, thus making swing currents and voltages to appear at once at all points in the circuit, must give way at high frequencies to the concept of waves traveling through connected cables in circuits upon times non-negligible with respect to the oscillation period. A signal of frequency f equal 50 MHz propagating at the velocity of light has wavelength equal to 6 meters. If we take a significant time delay of 1/30 of a period, we conclude that traveling wave technique should be used at such a frequency to deal with a phenomena taking place over distances larger than about 20 centimeters. In the figure, different transmission line structures are recorded, cylindrical in the left or planar in the middle in the right. Then there is the scheme of the impedance of the line. In the green box, the characteristic impedance of the line is expressed as a function of inductance L and capacity C, and the propagation constant is also a function of the angular frequency omega. When transmission line structures, for example the diameter of the connected cable, are significantly smaller than the signal wavelength, the analysis can be performed in terms of line voltages and currents. Most experiments involving transmission lines are nowadays performed using vector network analyzers. These devices have built-in signal sources and can measure the complex reflection and transmission coefficients of two-port and one-port networks over a broad range of frequencies. In the figure there is a sketch of two-port network. Port 1 is on the left, port 2 on the right, and you can see the reflection coefficient for port 1 S11, for port 2 S22, and the two transmission coefficient S21 and S12 between the two ports. The performance of such a network, that is, the quantities relating incoming and outgoing signals at the two ports, can be defined by means of the scattering matrix reported in the yellow box. It relates the signals entering and leaving the device under test through the reflection coefficients S11 and S22 and the transmission coefficients S21 and S12. In the figure you can see a basic scheme of a network analyzer. The swept radio frequency signal, typically from some 100 kHz to a few GHz, generated by a high-resolution synthesized source, can be delivered to either port 1 or port 2 of the device under test, DUT. Directional couplers separate incident and reflected signals. The signals leaving port 1 and 2 are routed to the inputs A and B of the receiver respectively, while the incident signal is sent to the reference input R. Transmission and reflection measurements can be done in both forward and reverse direction. The receiver has adapted ports A, B and R. In the yellow boxes you can see the expression of the reflection coefficient at port 1 to port 2 and the transmission coefficient for port 1 to port 2 and vice versa. The S1 is given by the ratio between the outgoing signal B2 and the incoming signal A1. In the same way, S22 is given by the ratio between B2 and A2. The transmission coefficient from port 1 to port 2, forward gain, S21, is given by the ratio between B2 and A1. And on the contrary, S12, transmission coefficient from port 2 to port 1, reverse gain, is given by the relation between the outgoing signal B1 and incoming signal A2. The input impedance of the transmission line can be expressed in terms of the reflection coefficient at the source plane, and is expressed in terms of S1N reflection coefficient for port 1. Now let's consider measurements on ring samples using a transmission line, which is the case of our ferrite sample. Coaxial lines are the seat of a well-defined field configuration and provide a convenient fixture for sample testing, in particular by placing the ring sample, as you see in the figure, at the bottom of a shorted coaxial line, where the electric field voltage as a node and the magnetic field current azimutally directed is maximum, we can ignore dielectric effects, provided the sample thickness H is small with respect to the quarter wavelength of the electromagnetic field. In green there is a direct network analyzer working between 100 kHz and up to 2 GHz, and we can measure the scattering parameter SR1 related to the impedance of the system where is inserted the sample. With the network analyzers, we can move the calibration plane to the desired location using internal software, which simulates a variable length transmission line and the related phase shift. We can thus compensate for the electrical length of the piece of coaxial line, separating the sample plane from the analyzer probe plane. The input impedance at the sample plane is given in the first yellow box. The input impedance is determined via the measurement of the scattering coefficient with and without the sample inserted in the line. The real and imaginary parts of the impedance difference are separated, and the real and imaginary permeabilities are thus obtained as expressed in the two yellow boxes. They are related to the geometrical parameter of the toroid, the external and internal radius, and the age of the toroid. The loss tangent is usually expressed as the ratio between imaginary and real permeability, and the Q factor is the inverse of the loss tangent. In these last figures, you can see example of broadband energy loss and permeability behaviors in nanocrystalline filament in figure on the left, and soft manganese zinc ferrite ring samples measured with in figure on the right, measured with combination of fluxmetry and transmission line experiments. In figure on the left, the colored line and symbol are the fluxmetric measurement, while the transmission line are the black points. And these is the energy loss behavior in filament. In figure on the right, we have the real and imaginary permeability on the manganese zinc ferrites M87 measured respectively at 2 millitesla red and 50 millitesla black. The blue points are the real and imaginary permeability measured using transmission line method. That means measuring the S11 scattering parameter.